The blast furnace, a big favourite with the examiners because it's one of the processes that's got lots of little details and equations and things going on. This is a classic site in the industrial lands of countries around the world. The blast furnace. Essentially, this is the motor for the production of steel, and it was the thing that was behind the Industrial Revolution. The idea of making lots of steel on a large scale, and you can make bridges and railways and ships, and it's very, very important in history. So it's quite a complicated little process, but it's very clever how the whole thing fits together. You need three things. You put three things into the top of the blast furnace. It's called the charge, and they contain iron ore, coke, and limestone. So the iron ore is hematite, which is mainly iron 3 oxide. Limestone, calcium carbonate mainly, and coke. And coke is coal that you heat in the absence of air. So you make the coal, which is mainly carbon, you make it pure by heating it to a high temperature with no oxygen, and it burns off all of the sulfur and phosphorus and anything else that's there. So hematite, iron oxide, calcium carbonate, limestone, and coke, and you put them in the top. They fall into the blast furnace, and the temperature as you go down the blast furnace gets hotter and hotter. Now there are 5 equations that you must learn, the big 5. The first one, the coke burns with the oxygen in a very exothermic reaction, which essentially is the thing that's heating the blast furnace and keeping the temperature so high. The carbon and oxygen, they react to form carbon dioxide, and that's an exothermic reaction. At these temperatures, the limestone decomposes, as we've seen previously, to produce calcium oxide, lime, and carbon dioxide. So plenty of carbon dioxide in there. Carbon dioxide from the first reaction and the second reaction, it reacts further with coke, with carbon, to produce carbon monoxide. And carbon monoxide is going to be the reducing agent of this particular process. Now before we go on to the next equation, hot air blast. Air is blasted into the bottom, a little bit like blasting air onto a barbecue. When you blast air onto hot coals, you give it more oxygen, then obviously the whole thing burns at a higher temperature, which is why it's called the blast furnace. The fourth reaction you need to know, and this is the reaction that produces the iron, is the reduction of the hematite. Iron 3 oxide, the carbon monoxide rips these oxygens off it, and you produce iron in its liquid form and carbon dioxide. Calcium oxide from the previous reactions is good at removing impurities from the blast furnace. There's lots of impurities in the ore, and we kind of signify these as silicon 4 oxide. So if the silicon 4 oxide is the impurities in the ore, it reacts with the calcium oxide to produce calcium silicate. And these silicates are also in liquid form. So they float on top of the iron in the blast furnace, and they can be skimmed off. This material, this mixture of the calcium silicates, is commonly known as slag, and it's used once it's solidified for the foundation of buildings and making roads. It's basically fairly useless, but it's hard and it can be broken up, so it's used in these contexts. The molten slag floats on the iron and is periodically removed. Okay, have a go at the questions on the pages indicated about the blast furnace. Stop me here and then we'll resume in a few seconds. Okay, once you've got the iron from the blast furnace, it's actually not very useful because it contains a high percentage of carbon and it still contains some impurities. So we need to reduce the percentage of this carbon, and we need to remove the rest of the impurities. So this iron is not particularly useful, it's not particularly valuable, and it's called cast iron or pig iron. Because of the high percentage of carbon, it's hard and brittle. So it's used, if it is used, it's used in contexts where strength is not that important, hardness is. So manhole covers in the street, gates, fences, etc., where it doesn't matter about the strength as much. And the hardness is actually quite useful. It can be bent and knocked into shape, so you can make big iron gates with cast iron. Steel, remember, is an alloy of iron mixed with carbon, small amounts of it, and other metals. So we need to make good steel from the pig iron. How do we do this? We pour it into an oxygen furnace. You'll find out why it's called an oxygen furnace in a second. We add scrap iron, which is recycled iron from car bodies, machinery, etc. We recycle that iron, so we throw that in and it melts. And we add a little bit more calcium oxide to remove any other impurities as slag. You know the equation there now. Silicates are formed by silicon 4 oxide reacting with calcium oxide. Then, why is it called the oxygen furnace? And this is an example of what it might look like. Oxygen is bubbled through the molten iron or blown onto its surface to slowly reduce the percentage of carbon. There'll be detectors to control the carbon content. So the carbon in the pig iron is reacted with oxygen and removed as carbon dioxide. And then at the end of the process, we throw in any other metals, nickel, chromium, etc., to make alloys according to the alloy that we're looking for. Important to realize that this is how iron and steel have been recycled for a long time. It's a large-scale recycling. And you get this metal, these iron and steel waste iron and steel from places like scrapyards, where you can separate the iron-based metals using an electromagnet, and they throw them into the oxygen furnace to be reformed. Okay, some more questions from Essential Chemistry there. You can stop me for a second. Right, alloys. As we've said, alloys are a mixture of metals and some non-metals too. Sometimes they might have carbon or silicon in them. So the key idea here is that the uses of the alloys depend on the properties we require them to have. This is where you're going to do a bit of research. So we can add a small amount of another metal, or carbon or silicon, and we can change its properties. What properties change? Well, typically the physical properties, like malleability, ductility, strength, conductivity, melting point. And you can see why the properties might be changed. If you can imagine, these are all my iron atoms, and this might be a silicon atom, this might be a carbon atom. Then you can imagine how this might affect how malleable this metal is, or it might affect how the sea of electrons can flow through it. Okay, so we play around with the properties to try and develop something that's useful. These are the alloys of iron that it's worth you remembering. So mild steel has got about 0.25% carbon, and we use it in car bodies. High carbon steel is harder, higher percentage of carbon, and we use it in cutting tools. And stainless steel with chromium and nickel is resistant to corrosion, and we can use it in sinks and cutlery and chemical plants. Right, there are some questions from Essential Chemistry there for you to look at on alloys. And you need to do a little bit of research now. So I want you to look up aluminium and you can look in the book or you can look online, the uses and properties of pure aluminium. So where it's used and what properties allow it to be used in that particular context. And then have a look at duralumin, which is an aluminium alloy. Look at what it's made from, what its main use is, and what its properties are. You can do the same for pure copper, and you can do the same for brass, one of copper's alloys. And then you can do it for pure zinc too. As well as for making brass, you can use zinc for other things. There's a little task for you to investigate the advantages and disadvantages of recycling iron and steel and aluminium. You can construct a table using or listing them. And then you've got plenty of questions from Essential Chemistry to finish off. And the end of chapter questions too. Okay, enjoy.